Welcome to the 19th lecture on complex variables and transforms, and in this lecture we'll study Laplace transform of integral of f of t, defined as f of tau d tau, and the range is from 0 to t. It is integrated from 0 to t, right? So in order to differentiate this t from this limit, the t in the limit from this variable, we introduce another variable tau here. But if we integrated this function and we put the limits, finally the function would be in terms of t, right? So that change of variable is only arbitrary. So but by definition we know that Laplace transform for any function is the same function times e to the minus st integrated from 0 to infinity, and these limits are for t from 0 to infinity. But here we have, instead of the function, we have the integral of the function. So we put the same, this whole here, we put this whole here. Instead of f of t, we put this integral here because we are going to compute the Laplace transform for this integral, right? Since now we have two integrals, this integral, the inner integral, whose limits are for tau, and these are from 0 to t. How do you know that this is for tau? Because we have d tau first in this line, along this horizontal line we have d tau first. Therefore the first integral will have limits of tau, and along this horizontal line we have dt coming after d tau. Therefore the outer limits, the outer integral, the limits of the outer integrals are for this variable t, right? So you know that the first, if you have only one integral, that defines area under the curve. But if we have this double integral, this means this is the area under some surface. So let's see what the surface is. The limits are for t from 0 to infinity. Let's draw these two variables on x and y axis. The t from 0 to infinity, so it goes from 0 up to infinity, where the limit for tau, the second variable, isn't from 0 to infinity, but it is from 0 to t. So this is the line t is equal to tau, and these, if we draw this surface or this surface as the horizontal lines, a set of horizontal lines, these lines originate from the y-axis, but they all end up at this diagonal line. If it would be from tau 0 to infinity instead of this t, that would cover the whole plane. Tau from 0 to infinity, t from 0 to infinity. That would be a very big rectangle or a very big square. But since we have these limits, the inner integral has limits from 0 to t. Therefore these horizontal lines, they end up at this line where t is equal to tau, this line with slope is equal to 1 plus 1, right? There is yet another way of describing this area, that is that we describe it with the help of vertical lines instead of horizontal lines. These are horizontal lines, but if we represent the same area with the help of vertical lines, that would tell us that now tau is going from 0 to infinity, because we have infinite vertical lines for all values, for all possible values of tau. But therefore we will have in this new integral, in this new representation, we'll have tau ranging from 0 to infinity. We have this tau ranging from 0 to infinity because we have infinite number of these vertical lines, one for each possible value of tau. But the limit for t is, it also goes to infinity, but it doesn't start from 0, whether in fact it starts from t. This is the line t is equal to tau. So now for t we have limits from tau to infinity. So each vertical line goes up to infinity, but the starting point is different for each line. The starting point for this line, this vertical line, is 0. Starting point for this vertical line isn't 0, but it is somewhat greater than 0. Starting point for this horizontal line is greater than 0, but greater than this line. So all these lines actually they land on this diagonal line with t is equal to tau. This means the starting point for each line is tau. Therefore, from tau, t goes from tau to infinity. So what we have done is we have represented this integral in another form. In another form, the thing that is written inside can also be rearranged, but the important thing is that we have represented this area as represented with the help of vertical lines instead of horizontal lines, and for that we have changed the limits of these two integrals. Although we have changed these limits, but the area represented is the same. The only difference is that previously we represented the same area with the help of horizontal lines, but now we are representing it with the help of vertical lines, right? So why are we going to represent this horizontal area represented with horizontal lines with vertical lines? We are doing it, we have done it to make things easier for us, to make evaluating these integrals easy, right? So how can we evaluate these integrals now? Right, let's take this tau is equal to 0 to infinity integral, the outer integral, and take this as the inner integral. That would take this d tau out and dt will be brought in, right? So we have replaced, or we have taken this inner integral out and this outer integral in. To do that, we'll have to interchange the position of these two integral, these two d tau and dt would be interchanged. This is what we have done here. Now we have dt written first and then d tau, because we have now the integral for tau written first and then the integral for t, right? And this integral is e to the minus st over minus s, and this integral has limits for t, and this is dt, so this whole integral can now be evaluated, and this and we know that the outer integral is evaluated after we have evaluated the inner integral. This is what we know previously, right? So this is minus 1 over s, and we put these limits e to the minus infinity minus e to the minus s. This t is replaced with this tau, the lower limit, and then we have this 1 over s taken out. E to the minus infinity, you know, it is 0, and 0 minus e to the minus s tau, and this is minus e to the minus s tau minus this minus multiplied with this minus becomes a plus, and we are left with e to the minus st here, e to the minus s tau here. This f of tau can also be written, either it can be written on the right or on the left, doesn't matter. F tau e to the minus s tau d tau, and tau from 0 to infinity. So by definition, if we change the variable from tau to t, if you want, you can have a change of variable here. Let's define a variable t that is equal to tau, and that change of variable will replace every tau with t. Every tau, these 4 taus will be replaced with t, and you see this is the definition for Laplace of f of t. So this is Laplace of f of t. So this is 1 over s Laplace of f of t. So we reach to the conclusion that Laplace transform of the integral of a function f of t is 1 over s, the Laplace transform of the function, right? So if you are asked to calculate the Laplace transform of the integral of a function, we have the Laplace transform of the function itself multiplied by 1 over s. That's a very important result, right? So now let's solve an example where we are given f of t to be e to the minus at. F of t is given to be f of t is e to the minus 80. Isn't it? It is not minus 80. In fact, I'm sorry. This is e to the 80. E to the 80. Right, and we are going to apply this result that we obtained in equation number 1, that we are asked to find out this Laplace transform of the integral of this e to the 80. And we know that by definition we have to compute the Laplace transform of e to the 80, and we have to multiply it with 1 over s. So we have multiplied 1 over s, and now we are going to compute the Laplace transform of e to the 80, which we know is 1 over s minus a, and which we can represent as 1 over s times s minus a, and let's call this result as a. Right, we can verify our result because we can compute. First let's compute the first compute the integral, and then we compute the Laplace transform. So that would of course be lengthier. It's a lengthy procedure and it's more complex than this, but of course we are going to verify our result, therefore we'll go through a longer path to reach to the same answer. 0 to t e to the a tau d tau, this one we need to first. Now we are going to first evaluate this integral, and then we'll apply the Laplace transform to reach to the same result as we reached in a. Right, e to the a tau divided by a is the integral, and the limits are from 0 to t, and 1 over a e to the a t minus e to the 0. This is the first limit put, this is the second limit put, the upper limit, the lower limit, and e to the 0 is a 1. We know that e to the 0 is a 1. So this is 1 over a e to the a t minus 1. And now we are going to find out the Laplace transform for this integral. And we know the 1 over a Laplace transform of, because constant e to the a t minus 1, and the linearity property says that this 1 over a can be taken out, and this Laplace transform for these two can be computed separately, and then they can be subtracted. So e to the a t, the Laplace transform of e to the a t is 1 over s minus a, minus Laplace transform of 1 is 1 over s, we studied previously, 1 over a, and then we compute the LCM of these two, and then right, and then we reach to the, after some calculations, we reach to the same answer as we reached in a. So a and b now are giving you the same answer. So this means that this is a very important formula, and with the help of this formula we can compute the Laplace transform of the integral in only one step, whereas otherwise we can reach to the same answer but with a lengthy procedure like this. Right, so it's a very important formula. We will use this formula in our next lectures. Previously we have studied the Laplace transform of derivative of f of t, and we derived, what did we derive? We derived that it is s times Laplace of f of t instead of 1 over s. So these two are very important results. The Laplace transform of the derivative is s times f of s, or Laplace transform of f of t, and the Laplace transform of integral of f of t is 1 over s times f of s, or 1 over s times Laplace transform of f of t. Right. So having said that, this is all for the 19th lecture, and we will keep on studying Laplace transforms in our next lectures. Thank you.